Throughout industry, gearing is used to transmit power from one turning shaft to another, sometimes changing the direction of rotation and sometimes changing the speed of rotation. Gearing is often used in applications where more power and precision is required than other power transmission drives can achieve. In this lesson, we're going to take a close look at gears. We'll see what kinds of basic maintenance they require and why that maintenance is so important if they are to provide long, trouble-free service. We'll look at some basic types of common industrial gearing, and we'll see how they are sized and selected for specific applications. We'll learn what problems to look for when inspecting a gear train, and we'll review the common procedures used to adjust, replace, and overhaul gear sets when they fail. The most important thing that you can do to maintain gearing is to keep it clean and lubricated. Enclosed gear reducers, or gearboxes, are protected by a heavy metal housing that's sealed and gasketed. Seals and gaskets keep out the dirt and grime common to industrial environments, and they keep the lubricant in. But an open gear train is exposed to the environment, so dirt and grime can get into the gearing and contaminate the lubricant easily. Even though most open gearing is housed behind guards and shields, the guards are mainly designed for protection of people working nearby, not to keep the gearing clean or to keep the lubricant on the gears. While dirt will not normally interfere with the immediate operation of the gearing, it can increase the load by filling up the clearance between the teeth, gradually damaging them by interfering with effective lubrication. Gear teeth that are forced too far apart by dirt will also put an extra load on bearings and shafts, contributing to misalignment and increasing wear. However, if gearing is properly sized for its application, if it is correctly aligned, and if shock loading is kept to a minimum, then gear failure will almost always be the result of a failure of the lubrication system. The lubricant got too hot, it was contaminated, or lubricant levels were too low for too long. If lubricant becomes contaminated by dirt, grit, grime, or water, it can quickly destroy the gears and may affect the bearings. The source of the contaminant should be identified and eliminated, and the lubricant should be changed. Nearly all facilities have a routine program for checking lubrication, whether it's just to spread on more grease, to fill up oil cups, or to check the operation of a pressurized lubrication system. If you perform routine lubricant checks, be sure to check for oil leaks. Leaking lubricants create a housekeeping problem, and they can be a fire hazard as well. A close examination of the gear teeth can almost always tell you a lot about any operating problems. The most common problems that occur as a result of improper sizing, alignment, and loading are pitting of the tooth surface and fatigue cracks at the root of the gear teeth. Gears are rated based on how badly they pit and how easily they crack. Some types of wear obviously mean trouble. Some of these teeth were badly bent, broken, or stripped off. The gear was seriously overloaded, far in excess of its rating. However, problems like this are usually preceded by signs of failure. When gearing is greatly overloaded, or when it is repeatedly overloaded to a lesser extent, it will often develop cracks at the base of the teeth. In general, you can expect that the life of a gear will be reduced by a factor of 8 if the full load is doubled. This means gearing that might have run reliably for 25,000 hours may break down in about 3,000 hours. Now, not all obvious wear is bad. There is a kind of normal wear that occurs when gears are operated at or near full load. The pattern of wear appears in the dedendum, the area below the midpoint of the tooth. It's called pitting, and it looks like a lot of small pits or holes in the surface of the tooth. If the pits remain shallow, and if they are all in the dedendum, and if the edges of the pits gradually wear down, then this kind of wear is considered normal. However, if the pits get deeper, or if the pitting extends beyond the dedendum, or if the edges of the pits do not wear down, then destructive pitting is occurring. The gear is on its way to failure, usually fairly quickly once destructive pitting starts. Many other kinds of wear can occur. It is often worthwhile to compare known kinds of wear to determine what may be going wrong. Standard descriptions and photographs of common wear patterns are available from many manufacturers and from AGMA, the American Gear Manufacturers Association. Now let's look at some of the common types of gearing, and let's see how they are sized and selected for specific applications. While there are many specialty types of gearing used throughout industry, the 4 most common types are spur gearing, helical gearing, worm gearing, and bevel gearing. Despite the differences among these types of gearings, they have much in common. If you understand how they are similar and how their differences suit them for particular applications, you'll be able to maintain and troubleshoot gearing in just about any situation. No matter what kind of gearing is used, the purpose is always the same, to transmit power from one shaft to another. One of the important considerations when originally selecting a gear type to use is whether or not the shafts are parallel. When they are parallel, then the choice will usually be a spur gear or a helical gear. If they are not parallel, then the choice will usually be a worm gear or a bevel gear. Other important considerations include the load on the shafts and the gearing, and the speed at which the two shafts must turn. For example, if the shafts operate at right angles, and if the load is heavy, and if the difference in speed between the input shaft and the output shaft is great, then a worm gear, like this worm reducer, would be used. But if the load is light and the input and output speeds are about the same, then a bevel gear, like this miter gearbox, would probably be chosen. Now, even if you never have to work up the design for a gear or gear train, it will still be helpful to know how they are selected and how they are specified. Let's take a close look at one gear, the common spur gear. We'll use it as an example to show you three major factors used to select gears. One factor is the gear's diameter, the distance from one side of the gear to the other. Most gears have a pitch diameter as well. It's the distance from the approximate middle of the tooth on one side of the gear to the approximate middle of the tooth on the opposite side. This is an important dimension because if two gears are to mesh properly, the total distance between their centers must be half the pitch diameter of one gear plus half the pitch diameter of the other gear. If this center distance, as it is called, is just a little too great, then the gear teeth will have too much play. They may clash against each other and wear out quickly. Or sudden shock loads or sudden reversals may damage the teeth or even break them. If the mounting distance is just a little too small, then the gears may grind against each other noisily, wearing away the lubricant and causing early failure. Gears may even jam together and lock up during operation. The pitch diameter is also important because in much of North America, the number of teeth per inch of pitch diameter is the primary method used to size gears. This number is called the diametral pitch. Usually, when people refer to the pitch of a gear, what they mean is the diametral pitch. Let's say you have a gear that's 10 inches in diameter, and it's got 10 teeth on it. Pretty big teeth. 10 teeth per 10 inches of diameter gives you a diametral pitch of 1. The pitch is 1. But if the gear is 10 inches in diameter, and it has 20 teeth on it, then the teeth must be smaller. But the diametral pitch is larger. The pitch is 2. If the same size gear has 40 teeth on it, the teeth must be even smaller, and the pitch will be larger. The pitch is 4. The way this works out is that as long as the pitch numbers match, the gear teeth will mate properly, regardless of the diameter of the gear and regardless of the number of teeth. Got a 6-pitch gear 7 inches in diameter and a 6-pitch gear 3 inches in diameter? No problem. The two gears will probably run fine together. We say probably because there's one other important factor that has to match before gears can really run together. That's the pressure angle. Pressure angle is easier to understand if you look at a rack and pinion gear set. Here's the pinion, a small spur gear, and here's the rack. Think of it as a curved gear that's been stretched out flat. See how the teeth of the pinion fit into the teeth of the rack? They fit this well because their pitches are the same, but also because this angle here, the pressure angle, is also the same. If this angle were different, then the gears would not mate correctly, even if they had the same number of teeth per inch. The most common pressure angle in use today is 20 degrees. The most common one used to be 14.5 degrees, like this. But the 20-degree pressure angle can take a significantly higher load because the base of each tooth is broader. Some gearing is available with a 25-degree pressure angle, and it can take an even heavier load. So the three main things you need to know when selecting a gear are the pitch diameter, the diametral pitch, and the pressure angle. You can usually identify the pressure angle if you have a manufacturer's catalog available. Check the numbers stamped onto the gear. For this manufacturer, the Y means the gear has a 20-degree pressure angle, while the N means the gear has a 14.5-degree pressure angle. Determining the pitch diameter and the diametral pitch may be just as easy. In some cases, they'll be stamped on the gear. If not, they can be figured out if you know two things. How many teeth are on the gear? Just count them. And the outside diameter of the gear, not the pitch diameter. Just measure it. Now, add 2 to the number of gear teeth and divide the sum by the outside diameter. Round it off, and that's the diametral pitch. Now take that diametral pitch, divide it into the actual number of teeth, and that's your pitch diameter. If you have 2 gears with the same pitch, then add their pitch diameters and divide the sum in half. That's how far apart the centers of the gears will have to be in order to mesh properly. Okay, let's run through it again. If you want to know if 2 gears can be used together, here's what you do. On each gear, count the teeth, add 2, then measure the outside diameter and divide it into the +2 tooth count. The number you get is the diametral pitch. If the diametral pitches are the same for both gears and if the pressure angles are the same, then the 2 gears will run together fine. If you want to know how far apart they should be mounted, divide the diametral pitch into the actual number of teeth. This gives you the pitch diameter for a single gear. Add the pitch diameters for both gears and divide by 2. The answer is the center distance for the gear set, that is, how far apart they should be mounted. Now let's look at helical gearing. Except for the fact that the teeth in the helical gear are set at an angle, it's a lot like the spur gear. One difference is that because of the helix angle, there are left-hand and right-hand helical gears, and they must be used in sets. When used to drive parallel shafts, the handedness of the 2 gears will be opposite. One will be a left-handed gear, the other a right-handed gear. When replacing one gear in a set, the easy way to tell whether the replacement has to be right-handed or left-handed is by laying the gear on a flat surface. The teeth on a left-handed gear will lean to the left, no matter which side you lay it on. Teeth on a right-handed gear will always lean to the right. Helical gears used on parallel shafts can generally handle larger loads at higher speeds than spur gearing of the same size, so they are often used in gearboxes, especially at the high speed end. Helical gears also usually operate more quietly. Helical gears are rarely used on shafts at right angles to each other because fewer teeth mesh and loads must be considerably lighter. Instead, when shafts are at right angles, a worm gear set is often used. This gear set consists of a worm with screw-like threads, or starts, that rotate on a toothed worm wheel as the worm turns. Unlike most gear teeth with rolling contact that produces comparatively little friction, the threads of the worm and the teeth of the worm wheel slide along each other. This creates a lot of friction and heat that often makes worm gearing operate hotter and less efficiently than other types of gears. However, worm gears are often used because they are compact. They can transmit a lot of power, and they can have large gear ratios, as high as 100-to-1 or more. Gear ratio refers to the relationship between the speed of the input shaft and the speed of the output shaft. For example, a gear ratio of 100-to-1 means the 100 revolutions of the worm will turn the worm wheel around just one time. The ratio for most gearing can be determined by comparing the number of teeth or by comparing the diameters of their pitch circles. For example, a gear with 84 teeth meshed with a gear that has 42 teeth will have a gear ratio of 2-to-1. Their pitch diameters will also be 2-to-1. This gear has a pitch diameter of 7 inches, while this gear has a pitch diameter of 3½ inches. The ratio of a worm gear set is determined differently. The ratio is equal to the number of starts or threads on the worm divided into the number of teeth on the worm wheel. You can determine the number of starts by looking at one end of the worm and counting them. Just as with helical gearing on shafts at right angles, the worm and the worm wheel must be of the same handedness. You can determine the handedness of any worm or any worm wheel just as you do with helical gearing, by laying the worm or the worm wheel down flat. The threads on a worm are like the threads on a screw. The threads of a left-handed worm slant up to the left, no matter which way it is turned. The threads of a right-handed worm always slant up to the right. Like a helical gear, the teeth of a worm wheel will seem to slant to the right or to the left, depending on the handedness. Now let's look at the fourth basic type of gear, the bevel gear. Bevel gears are used when two shafts are at an angle to each other. However, bevel gears are usually used at relatively low speeds and for relatively low gear reduction. Bevel gears often come from the manufacturer in matched individual sets like these. Because they are finely ground and polished or lapped to run together precisely, they should always be installed and replaced as sets in order to assure proper operation. Bevel gears require precision mounting. Now, all gears must be mounted carefully, but some require more precision than others. Spur, helical, and worm gearing all have a center distance, which is based on pitch diameters. We discussed this earlier. Bevel gears are different. As an example, each of these gears has a mounting distance. The distance for this gear is equal to the distance along an imaginary line passing through the center of the bore and extending until it meets another imaginary line passing through the center of the bore of the other gear. The point where the two lines meet is called the apex, and it will be different depending on the size of the gears. The installation, adjustment, and general maintenance of all gearing may require a great deal of precision. During initial installation, center distances, mounting distances, and other factors such as axial float and bearing preload may all have to be held to very close tolerances, often as small as a few thousandths of an inch. Failure to set the correct distances may cause the gearing to grind together if the distances are too small, or may cause excessive backlash if the distances are too great. Backlash is the term used to describe the clearance or play between gear teeth when they mesh. All gearing should have some backlash in order to provide space for the lubricant required during normal running. Oil must not only lubricate the face of the teeth as the gears turn, but there must be sufficient clearance for the oil to move along the bottom of the tooth. If the center distance or mounting distance of the gear pair is too small, oil will become trapped at the root of the teeth, and the gear may overheat, especially at higher speeds. Normally, backlash is not set directly. Instead, gears are manufactured so adequate backlash will exist when the gears are mounted the correct distance apart. However, the backlash can be checked by using feeler gauges if the recommended backlash is relatively large, or with a dial indicator if more accuracy is required. If backlash is not the same in all gear positions, the shafts and the gears may both require alignment or other adjustment. Usually, feeler gauges, dial indicators, and similar methods are used only for large gearing. Very fine-pitched gearing requires other methods which measure the operating error of the gearing. If the gearing is to provide long, reliable service, certain practices and procedures should be followed. The most important of these, as we said before, are cleaning and lubrication. But correct installation and careful maintenance over time is also important. For example, when gearing is repaired or replaced, it may be necessary to rebore the hub, to add keyways, or to add set screws to the hub. The most important consideration when undertaking any of these alterations is to make sure the new bore is concentric with the original bore, and that no wobble is introduced in the gear. In general, bores should never be enlarged to more than 60% of the diameter of the hub. Another critical factor is the alignment of the shafts and the gears themselves. Shafts that are misaligned may cause gear teeth to be overloaded because the load will not be properly distributed across the teeth. Shafts and gearing which are correctly aligned during installation may become misaligned due to heavy loads which deflect the shafts, from thermal expansion of shafts, or the gearing during operation, or from wear on the gear itself. Shafts may also become misaligned as a result of bearing wear. Most gearing produces thrust loads on the bearings that support them, often in two directions at the same time. If the load becomes too great, or if a change in an application requires a change in the direction of rotation, bearings may become overloaded. For example, if the worm in this left-handed gear set operates in this direction, then the bearing on this end of the worm gear must be a thrust bearing, while the bearing at the opposite end need not be. However, suppose the driver motor is rewired to meet the needs of an application that now requires rotation in the opposite direction. Now, the thrust produced by the worm, which can be considerable, will be applied to a bearing not designed for thrust loading, and the bearing may wear out very quickly. For proper operation, the bearing should be switched or a different gear set used. The same thing is true of the bearings on the worm wheel. Comparable changes may have to be made when making alterations to helical and other kinds of gear drives. For example, when the lower right-hand helical gear in this gear set drives the upper left-hand gear in this direction, the gear assembly will require a thrust bearing on this end of the driver shaft and on this end of the driven shaft. But if the direction of rotation is reversed, the thrust bearings must be relocated to the opposite end of the shaft. Similarly, if the driven shaft is switched, then the bearings must be switched. For helical gearing used on parallel shafts, end thrust will be in the same direction as the hand of the gear when used on a driver shaft, but in the opposite direction of the hand of the gear when used on a driven shaft. Many gear manufacturers include a complete explanation of such matters in their catalogs. In this program, we've seen some basic types of common industrial gearing, and we've seen how they are sized and selected for specific applications. We've learned what to look for when inspecting gear, and we've seen some of the common procedures used to adjust, replace, and overhaul gear sets when they fail. If gearing has been correctly sized and installed, and if it is not overloaded, following basic maintenance practices will minimize downtime when things do go wrong, and it will help to ensure long, trouble-free service.